Yeah, don't. I prefer you open the microphone than that you send me because the noise blah 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 of the chat. Okay, entonces la idea es clear. La idea es vector value function es a function, multivariable function, que the input es one scalar t. T no necessarily is time, guys, it's a parameter. And the majority of the application in physics, of course, time, but generate a vector in 3D que have three components, x, y, and z, que es each component is a function, it's a scalar function, but all together represent the vector value function. So the vector value function is a vector in 3D or in 2D maybe, que is a variable. And represent is the fantastic way to represent a curve in 3D because any point you associate with the position vector. Okay, entonces now this is a function, and the function we can apply calculus, and the calculus that you can apply in this vector value function is the calculus that you very well know. Limit, derivative, antiderivative, etc. Okay, look. Let me see. The position vector que is equivalent to displacement is one interpretation. Displacement is R of any time or any t is x of t, comma y of t, comma z of t. If you find the derivative of this, the derivative of this vector value function, let me use this notation, prime. We can use another, but this is, entonces now it's velocity. And velocity is a vector. And velocity is, in any point, is tangent vector. Velocity. Is it velocity? Okay, let me write velocity. Bueno, velocity in word, but velocity in letter like that. So the first derivative of displacement is velocity. And velocity we compute like that. You differentiate component by component. Xt prime, comma y prime t, comma c prime t. Okay, it's a vector. It's another vector value function, but in this case, this vector value function in any point is no position, is velocity, therefore is tangency to the point. Now acceleration is second derivative. Acceleration is the second derivative. Second derivative of t is acceleration, que es also vector. Yes, you differentiate component by component 2 times. Second derivative. Acceleration, well, I don't know exactly the position in what direction point. Let's see after the application. Acceleration. Now, one more. In 3D is important, the jerk. What is the jerk? Okay, nobody using jerk in physics. It's the third derivative. The third derivative is the jerk vector. This is important in the equation that we see after that. So it's the same. Third derivative each component. We need to use third derivative in 3D. Okay, now what about speed? Well, speed is you take velocity and you find the absolute value. So magnitude, velocity. Velocity is a vector, speed no. Speed is a scalar, it's a scalar function. And as always happen, it's a square root. Each component, x prime is square, plus y prime is square, plus c prime is square. This is a speed. Speed is a scalar function. no vector, no indicate direction, only vector. Some people prefer, for example, calculus 2. The teacher of calculus 2 prefer that notation. It's the same, and maybe it's a little bit familiar with you. Dx dt squared plus dy dt squared plus dz dt squared. And this is speed. Okay? Now, if you integrate the speed, so integrate from A to B of the speed, okay, speed is absolute value of the r prime t, absolute value of magnitude, no? dt, is the distance, or r length, distance travel, or r length, because we travel along the curve, no? One more popular equation, formula that we use in calculus 2 is integral from A to B over the square roots dx dt squared plus dy dt squared plus dc dt squared. And don't forget everything inside the square root, because this is speed, huh? dt. Okay, this is r length. Entonces you see very well the advantage to represent the curve in that way, is the space curve and t is the parameter. Entonces we studied a lot of things.
At the bottom, does arc length equal distance traveled, or does arc length equal L?
Yeah, of course. Arc length equal L, capital L. Arc length or capital L or distance traveled, it's the same. So basically,
they're all the same.
You have the curve. We have 2 points. This is t equal A. This is t equal B. And when you plug it in the formula, you obtain that distance. Right? Could be distance. Are you familiar with this formula? Yes or no?
Yeah.
Yes, no new for you. Okay, just let me reinforce the concept of the parametric. We studied in detail parametric. Guy, I sent to you today this page, right? For this page you see now. Okay? Let me see now parametric in 2D y parametric in 3D. So it's extremely important for me that you understand very well parametric. So basically, we are working with the curve. Curve obviously is one linear, one dimension object. Okay, well, the topic I want to study now is parametric. Parametric we study in pre-calculus, but I want to recall because it's important to make sure that you understand very well. Parametric in 2D. Parametric equation, no? Parametric equation in 2D. 2 dimension. Let me study 2 dimension first. After 3 dimension, it's a little bit more complicated, but not too much. So now, suppose this equation. Example 1, easy. Suppose x squared plus y squared equal 4. It's obvious, everyone recognizes that this is a circle. This is a circle where the center is located at the point 0, 0, and the radius 2. But the parametrization is, okay, for example, you remember, the parametrization is not unique. You can use it different way. In this case, the most common way is you divide by 4. our original equation. Because somehow I need 1 in the right hand side. And you copy x squared over 2, no, x squared, no, x over 2 squared. You have x over 2 squared plus y over 2 squared equal 1, right? Entonces I suppose, hypothetically, you remember in trigonometric this famous identity, trigonometric identity, que es cosine square any angle, let me call t, plus sine square t equal 1. Wow. Entonces, if you define que x over 2 is equal cosine t and y over 2 is sine of t, and then satisfy perfectly this. Therefore, in parametric, x is equal 2 times cosine t and y is equal 2 times sine t. You want to represent like a vector value function. Okay, let's do it. Vector value function que represent that curve in 2 dimensions is R, like a vector value function of t, is you open the angular bracket because it's a vector, 2 cosine t, comma 2 sine t. Wow, fantastic. This is the new idea of the parametry. You write like that, or you write like that. What is the advantage? Que you consider like a parameter, not 2 equations, one function, que es vector value function, and you can differentiate, integrate, everything in calculus, right? Super important this idea I want to discuss. Okay, this is a circle. Okay, this is a parametric that represents this curve. Okay, let me try to do my best. The circle is radio 2, 1, 2, 1, 2, 1, 2, 1, 2, and center and the origin, something like that. This is x-axis and this is y-axis. Remember, in parametry you have to define not only the equation, you find the domain. It's super important, domain of t. Domain of t, in that case, is bracket 0, 2 pi. It's clear because this is the closed curve. Entonces now, pero es important, for example, evaluate en 0. You evaluate the vector value function in 0. We have 2, 0. Because cosine 0 is 1 and sine 0 is 0. And you plot this point, or this vector, que es the same, is this point. Okay, the point is 2, 0, and vector is like that, 2, 0. Suppose in pi over 2, okay, in pi over 2. And pi over 2 would be cosine pi over 2 is 0, and sine pi over 2 is 1, so 1 times 2 is 2, and the point is like that. This is the point, 0, 2, and the vector is exactly the same. Position vector. We are talking about so far position vector. And so you continue evaluating pi, and 3 pi over 2, and 2 pi, when we rotate in this direction, and come back to this because it's closed. So it's super important, guys, when you are doing this orientation idea. Our orientation is in this direction. In this direction. In this case is counterclockwise. Always is like that. No. So you change the vector value function, that is possible. For example, interchange. You put it here, for example, what is the reason I define this like a cosine? And it's not because I like, but so you define in different orders, you interchange this guy. So you have 2 sine t, 2 cosine t. Okay, entonces now it's the same curve. Of course, it's the same curve, but the only thing that changes is the orientation. because in the new vector value function, well, the number is switching, no? Entonces now the orientation is no control go Y, is scroll Y. Do you understand this or no? Do you understand this or no? Come on, guys, answer me. Yes, no? Yes, Theo say yes. Okay. Okay, this is easy example. It's the first one. Of course, it's always the first one is easy. Let's move on to example 2. More a little bit more complicated, but it's no big deal. Example 2. Example 2 is that curve. X squared plus 2y squared minus 2x plus ay plus 1. And remember, guys, we are working now in 2 dimensions. No en 3, en 2 dimensions. Entonces, dice, I suppose que es the conic section, ¿no? Es the conic section, you complete the square, classical example, x squared minus 2x plus box. Plus 2 times y squared plus 4y plus another box equal, wow, negative 1, I move to the right hand side, plus 2 box. And the number to complete the square here is 1, it's obvious, here 4. You put in then 1 here, and you put here 4. 4, no, 8. 8 because it's 4 times 2. The factorization of this trinomial is x minus 1 squared plus 2 times y plus 2 squared equal 8. Entonces, now I understand a little bit clear. You divide by 8, everything. It's exactly the same we are doing in the surface, but now it's in 2D. So we have x minus 1 divided by square root of this guy gets 2 radical 2 square is equivalent plus y plus 2 divided by 2 because it's 8 divided by 2 is 4 and 2 square is 4 equal 1. Ready to represent in parametric after in vector value function. I call x minus 1 divided by 2 radical 2 like a cosine t. Y I call y plus 2 divided by 2 like a sine t. Yeah, I know very well that cosine square plus sine square is equal to 1. Matching perfectly. Now the parametric equation are, so for x is equal 2 radical 2 cosine t plus 1. You solve for y, no? You move this multiplication, pass, bring to the other side 1 positive, and likewise, y is equal 2 sine t plus 2, or minus 2, sorry, minus 2. Okay, this is a parametric. T is again between 0 to pi because it's a closed figure, it's elixir, no? It's elixir. This is, you see that, you understand que es elixir? Elixir with the center is located at the point 1, comma negative 2. I suppose que A is 2 radical 2 and B is 2. The major axis, our elixir look like that. Horizontal elixir. And this point is this point. Okay, so you want to represent like a vector value function is angular bracket 2 radical 2 cosine t plus 1, comma 2 sine t minus 2. And the same specification of the domain. T is this. Cool? 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 Okay. Let's move to another example. This example is a little bit more complicated. is, you know, x minus 2 squared, make it soon, divided by 4 minus y minus 3 squared divided by 16. Okay, using our knowledge of the conic section que we studied in precalculus, you identify que es the hyperbola. Hyperbola with the center of the hyperbola is located at the point 2, 3, okay, h and k, and a is 2 and b is 4. Remember the hyperbola, guys, a is not the bigger, no, a is the guys, the term que is positive, because our hyperbola, by the way, the center is located here, 2, 3, is like that. Bam, bam. The transversal axis of the hyperbola is parallel to the x-axis because x is a positive, right? Okay, this is a quick review about conic section. We have more detail. We have asymptote, but it's not important. Now I want to find parametric. So parametry, I need to remember something. Es obvio que the fórmula cosine square t plus sine square t doesn't work because this is 1, no plus. This is negative, no positive. So no, not good. But we can using coach. I don't know if you see before the teacher in square, the teacher in Cal 2 explain hyperbolic trigonometric function. The majority of the teachers don't explain that. Do you see coach and sine? Or never you see that? A ver, no. Okay, David, no problem. No problem. The majority of teachers don't explain. I don't know why. I don't know what happened in the United States. But this is a function, a hyperbolic function. Never. Wow. I don't want to explain now because it's Cal 3. But don't worry, I am using another. Remember, the parametrization is not unique. So we can, si you don't understand or you never see this function, no problem. I have another trigonometric identity you very well know, que es secant square t minus tangent square t equal 1. Do you see or no? Yes. Entonces nada, ahí declaré, bueno, que x, ahí declaré que x over 2, x minus 2, sorry, divided by 2 square, minus y minus 3 divided by 4 squared equal 1. And you declare que this is secant, and you declare que this is tangent. Entonces, our parametric equation is x over 2 divided by 2 is equal to secant t. And likewise, y minus 3 over 4 is tangent. Therefore, so for x is equal to 2 secant t plus 2. And y is 4 tangent t plus 3. And this is the set of the parametric. Okay, I need to specification the parameter. Don't forget, when you leave it like that, this is a totally incomplete idea. But the vector value function associated with that is 2 secant t plus 2, comma 4 tangent t plus 3. Entonces now the hyperbola, guys, let me specification the t now. The t is a little bit complicated. But in the hyperbola, remember, this is no closed curve, like helix is completely extended forever, no? Extended forever. Extended forever. So now, let me try to use my knowledge of the trigonometric. I remember very well, that, for example, the cosine function look like that. This is 0, this is 1, this is pi over 2, this is negative pi over 2. This is cosine. The reciprocal of cosine x, is secant, 1 over cosine. And the curve of the secant is reciprocal 1 is 1, and here is 0, so it's undefined. We have here a vertical asymptote. This is approximately the shape of the secant. This is secant x, secant t, whatever. And the tangent, is different. The tangent 0 is 0, tangent pi over 2 to be undefined, and tangent minus pi over 2 to be undefined. Tangent is like the green part. So one good selection of the parameter is t in between. Well, actually do not include because it's undefined. So it's no bracket, parenthesis, minus pi over 2 to pi over 2. Unbelievable, this interval cover any branch of the hyperbola can go to positive infinity or negative infinity, no? Go positive infinity or negative infinity. Guys, the fantastic way to see that in GeoGebra, I want to show you now, is using one function that we studied before, is a curve. So you in GeoGebra, in one line of the GeoGebra, you put curve, and you put, open the parenthesis, and you put expression of the vector value function separated by a comma. Look, you put here x to t, y to t. In this case, 2 dimensions. To say no, we have no z. No. 2 dimensions or 3 dimensions. Either way. We studied today both, no? Pero so far it's 2 dimensions. Coma t, que es el parámetro, coma the interval, que es minus pi over 2. And pi over 2. For example, in this example. And you see the hyperbola. Wow, fantastic, right? I want to show you in a few seconds. Entonces es super easy verification. Our job, because you open your algebra, you put the function curve, que es somehow equivalent to the vector value function. It's another way que the software, the GeoGebra describe vector value function. The mathematicians see and the paper no, is vector value function, and GeoGebra is like that. Cool. Let's see one more example in 2D, and after we see example in 3D. One more example in 2D. Example 4, no? Example 4 in 2D is this one. Example 4. Example 4 is x minus 3 squared equal 4 y minus 1. Whoa. I immediately recognize this curve. This is parabola. What kind of parabola? Well. Before it say what kind, I see what is the vertex. And the parabola have no sense to talking about center. It's vertex. And the vertex is located at the point 3, 1, no? This is H, and this is K. And this parabola open up is vertical parabola. So at this point, it's supposed to here, and the parabola open like that. Because it's vertical parabola, no? How do you know it's vertical? You have two kinds. The vertical the equation is x squared equal 4py. Si we have translation, entonces x minus h squared equal 4p y minus k. Si square es y, entonces es horizontal. Pero no, it's not the case. The traditional way to parametrization, there are many ways. Remember, I repeat one more time. Parametrization is not unique. Parametrization depends on the equation you're using, the selection that you're using, and the parameter that you define. In this case, in my paper, I define x minus 3 is t minus 3 is t because I want. Okay, and the moment I did that, I like this. Now, you select here x is equal t plus 3, and you may be plugging in so y, this is t squared, is equal 4 parenthesis y minus 1, you distribute it at 4y minus 4, no? And you solve for y. So it's t squared plus 4 divided by 4 and y. Entonces, what is the set of the my parametric equation? Well, the set of my parametric equation is x equal t plus 3 and y is equal t squared plus 4 divided by 4. Okay, don't forget the interval of t. Okay, but before I analyze that, I like write like a vector value function. Vector value function is two components because it's two dimensional. The first one is t plus 3, and the second is t squared plus 4 over 4. And this is the parabola. And it's obvious that TS go from negative infinity to positive infinity. Guys, this is not new for you. When we study the line, you define the parametric equation of the line and you define the interval. Okay, the line is infinity, no, in both directions. There is the reason okay, from negative infinity to positive infinity. The parabola is also infinity in both directions because the parabola continues forever. It's different to the elliptic. The ellipse is closed curve. But, you know, depending also the formula is more complicated than this because in the hyperbola we studied before is not closed. However, the t domain is bounded between negative power 2 and positive power 2. Cool? Cool? Now, nice. Yes, okay, no problem. Let me try to show you quickly, of course. The time is our enemy, you know. The algebra I create there you go. Let me try. Okay. Parametry in 2 dimensions. There you go. Pongo. Okay, there you go. Let me share the screen. Parametry in 2 dimensions. Do you see that? Do you see that? Tell me. Do you see it? Okay, yes. Okay, super. So now I try to do the same example. No? The function we have at the beginning is cosine and sine, amplitude. Okay, now this is the parameter. Look at that. This is the most important moment. The parameter we're using the function curve. You put the function t. Okay, you declare it before. You declare f like a 2 cosine and g like a 2 sine. No? So you put f and t. Basically, the function replace no x anymore. T is our variable. T es our parameter, and between 0 to pi, entonces es a circle. Wow. You delete this is the equation, and this is the circle. Exactly what you expect. Super cool. Super. But it's super easy also. Now, and the second example is h and p as a function is 2 radical 2 cosine x plus 1 and 2 sine x minus 2. And when you are doing the parametric Helix, by the way, the center of this helix is 1, -2, remember, right? Okay, super cool. And the third example is the hyperbola. We have the functions 2 secant, wow, weird. And 4 tangent, wow, weird. But I don't care this. I care the parametric. Is this I specification? Well, I specification. Look, I specification different parameter from 0 to 2 pi. Okay, in the paper I put negative pi over 2. But you see it doesn't matter. It's Helix. And by the way, you see that the Helix have the asymptote. But I don't do the equation for the asymptote. No, entonces, what is the reason that I see the asymptote? I suppose that when you travel in this direction and you go to infinity, and you return in opposite direction, entonces it's doing the infinity. Entonces, the GeoGebra understand that this is the one entire curve. It's amazing, really amazing. And the center is located at the point 2, 3. Look at that. Okay, super. Now the last one is a parabola. The parabola is this parabola. I suppose that this is different example because the point is 3,0, no? 3,0, 3,1. I make a mistake here. Don't worry, it's similar. We fixed that. So x is equal to t minus 3, no? Well, I did different. I did another example. And I did create because it's not simultaneously when you are doing the lecture and when you are doing the script. Okay, different example. It's a parameter. It's parametric of the parameter. Okay, let's come back to the whiteboard. Do you understand the idea of the parametric? Entonces, important thing that the student frequently forget. Parametric is a set of 2 equations in 2 dimensions or 3 equations in 3 dimensions. You need the specification also the parameter, so the domain of the parameter, and you need to specification also the orientation. The orientation. Sometimes it's important, sometimes it's not extremely important, the orientation, no? Pero es one idea behind it. Okay, let me try now. See, you have no question, no? You have to see the problem in 3 dimensions. Clear or no? Yeah, I suppose yes. Suppose in 3 dimensions, as always happen, this is classical guy. When you increase in the dimension in mathematics, the complexity is higher. Suppose that we have a plane. Suppose that we have a plane. And that case is one plane is c equal constant, c equals something, c equal 4, a constant, and we have cylinder. Like that. I try to do my best. Huh? And the intersection between the plane and the cylinder is a circle. It's obvious, no? But a circle in 3D, right? Entonces, to define the parametric, this is my goal, parametric equation for this. Parametric equation for this circle. Well, entonces I take advantage the vectorial, no? I can, for example, I have the center. The center is super easy to find. because I have the equation for the cylinder. Suppose que the center, this is R null. Entonces R null is X null, Y null, Z null. Like a vector, right? And we have, similar to the thinking we are doing in 2D, we have this vector and this vector, and the equation is in general, say R, let me use in black column, R to any point, R is equal R null plus something. And this something is another vector que es rho cosine t, coma rho sine t, coma 0, because we are in this plane. In this plane, when we have nothing, and so the component C is this. So you separate in two components, the X, so remember, who was R? R is X, comma Y, comma Z. Entonces, X is equal a X0, que es this, plus rho cosine T, que es this component. Y es Y null plus rho sine T. And C have no component here, 0 is 0. Wow, fantastic. This is the set of the parametric, and T, of course, vary from 0 to pi. And you describe the circle. That circle, okay, that circle is in 3D. Now, one fantastic way to write a vector value function. Oh, this is one possibility, but more elegant is, look, R vector value function T is equal R null plus rho, que rho is the radio, guys. Rho is the radio. What is the reason, professor, you call rho and not R? Because confusing R with another letter R. So I call rho is the radio, is the distance. Is the distance, rho. I call another, or capital R, whatever, this is another letter, rho. Entonces, rho what? Rho 1,0,0, que es I. This is I, the classical orthonormal vectors. I, que I is in the direction of the x-axis. So this look like the par in the direction, cosine t. So basically, our equation, you can write like that, plus rho 0,1,0 sine t. Oh, more elegant, you know, this is cosmetic part, is rho I cosine t, sorry, this plus. This is R. Cosine t plus rho J. This is J. Sine t. Okay. You see it's a little bit more complicated. We're using vectorial notation. It's obvious, no? In 3D, always we use vectorial. But this was the easy case in which the plane is parallel to the XY plane. Pero suppose que no, que it's not parallel. Suppose another scenario in which, don't worry too much. You see que, I explained this, but you see que this is relatively easy. At least in the example. There are another example that is horrible. But in the majority of the example, it's no big deal. Suppose que now we have a plane que is a little bit inclined. slam. And we have again our famous cylinder. I select cylinder because it's easy to see, but not necessarily cylinder. It's the intersection between plane and maybe cone, and maybe another plane. So we have here no circle anymore. No. We have helix set. We have helix. Entonces now it's a little bit complicated to find the helix. In this case, we have two radio, no? This radio, okay, called row 1, and we have another radio here, row 2. I call row 1 in the direction of the x-axis. This is row 1, sorry. And the direction of the y row 2. So the formula is similar. Suppose in this case the normal vector is this vector, normal vector, perpendicular to the plane. Entonces now I cannot use in the regular trihedral IJK because our plane is a little bit inclined, but no problem. I try using another vectors. Entonces now in this case I can find the unit vector here. Okay, I want to call no case, K prime. Entonces we have I prime perpendicular to this, and parallel to the x-axis is I prime and J prime parallel to the y-axis. Entonces the equation is R in vector value function, ¿no? Is equal R null, que es relatively easy to find the center of this because actually it's a coincident with the center of the cylinder, no? R null plus row 1 I prime cosine t, similar idea, plus row 2 J prime sine t. The challenge is who is I prime? Jeez, where come from this? And J prime. Well, it's no big deal. Suppose that you determine 2 points on the helix, this and this, or this and this, much better in that direction. And then this is parallel to the x-axis. You have 2 points, so it's easy. When you have 2 points in that direction, you determine the vector in between 2 points, and also using the formula, we found the unit vector in that direction. And this is I, boom, or J, either way. And the J prime, this is prime. The J prime vector is equal K prime vector cross product I prime vector. So you have in your hand I prime using 2 points. You perform cross product. Oh no! Or you find another 2 points in this direction, is the direction of the y, and you determine J prime. And you find this in vector value function. Okay, this is the let me explain in one easy example. You see, wow, too much complicated. No, it's easy. Let me show you in detail now. Okay, look, suppose I need to find the parametric equation. This is example number 1 in 3D. Example 1 in 3D. Suppose that we have x squared plus y squared equal 9. And suppose that we have x minus y plus c equal 4. Entonces our curve in 3D space is the intersection this surface. Surface 1, surface 2, and our curve, I want to find the parametrization is intersection between surface 1, intersection surface 2. Do you understand the idea? Do you understand the idea? Answer me. He said no. David said no, question mark. Okay, the thing I try now, David, is we have two surfaces in three-dimensional space. The first surface and the second surface, surface 1 and surface 2. And the intersection between this surface is a curve. Similar to the example that we are doing before, no? I put a plane, I put a circle, cylinder, sorry. And the intersection, I have no idea. Maybe it's helix or maybe it's, I don't know, it's parabola or something, right? So now I need to parametrization this curve, and also I want to express it like a vector value function. Good? Okay, it's no big deal. Do you understand? Okay, David, understand. Okay, so I have a question for you, for David, for everyone. What is the first name and last name of the surface 1? It's x squared plus y squared equal 9. I suppose que you know surface. What is that? What is that in 3D? No in 2D. Answer me. Come on, guy. Participation. Is yes. No, the answer is no, yes. Ernest, the answer is no, yes or no question. Is what is the name, first name and last name of the surface 1? Que es x squared plus y squared equal 9.
Ellipsoid.
Elixir? No. Elixir, no. Okay, good. Surface, elixir is no surface. Elixir is a curve in 2D. We are talking about now in 3D. In 3D, x squared plus y squared equal 9. What kind of surface it is? A ver, cylinder. No, no parabolic. Hello. Es circular cylinder. Okay. Okay, in 2D, x squared. What happened, guys? Well, x squared plus y squared equal 9. In 2D, it's a circle where the center is in the origin and the radius 3. End the story. In 2D. In 3D, no, because Z is missing. If Z is missing, this is extending forever along the Z-axis, and this represents a cylinder. And I promise that you see in few minutes this in GeoGebra, right? It's a cylinder. Cylinder. Last name is circular cylinder. Circular cylinder is the name of this surface. And what is the name of this surface? X minus y plus c equal 4. What name? What is the name? What is the name? What is the name? X minus y plus c. Come on. I waiting for the answer. Come on. X minus y plus c equal 4. I suppose you know. Si you don't know, you are in big trouble. Nobody know. Wow.
One sheet.
Well, no, please, no. Okay, to be hyperbolic, you need a square. You need a square. A square. Entonces I agree with you. Okay. Listen to me. It's important that from now you recognize, because in the chapter 2 and the chapter 3, we working every day with the surface, and you need to know very well surface. Recognize, we are working. This is a plane. How do you know que it's a plane? Because because the exponent is 1, it's linear, it's flat. Okay, when the exponent is 2, 3, 4, 5, entonces es little bit curvy. It's a surface, but this is a stupid plane. Hello. I was going to say, yeah, I wasn't sure. Okay, no, okay. You are a student, you are learning, but in one moment, you need to know. Okay, the classical equation that we study of the plane is this. By the way, you know this in pre-calculus. Okay, in this case, A is 1, B is negative 1, and C is positive 1. And D is 4. Yes or no? Yes or no? Entonces, ok, entonces We have in this problem cylinder and a plane. Okay, cut off the cylinder. This plane is a little bit inclined. Therefore, in my intuition, I suppose que es Helix. Pero Helix en 3D, que es no totally, it's a little bit slamp, right? Okay, so now, the parametrization, in my opinion, is too easy. Why? Because you take advantage again, okay, x is equal, look, you divide by, you take x squared plus y squared equal 9, divided by 9, divided by 9, divided by 9, y over 3 is squared plus y over 3 squared equal 1. And you define x is equal 3 cosine, cosine t. Y is equal 3 sine t. And what about z? Well, I have no idea. But remember the intersection between the surface. So the common point in the cylinder is the common point in the plane. No? So you isolate z in the equation of the plane. Z is equal 4 minus x plus y. No? Therefore, Z is equal 4 minus 3 cosine t plus 3 sine t. Wow, this is the set of the parametric equation of this surface that is in 3 dimensions the intersection between two surfaces. And this is no surface, it's a curve. And curve is obvious que es one dimension object. This is surface two dimension object. And the intersection to surface is obvious que es one dimension object. It's a curve. It's a one dimension. Of course, when you're talking about dimension, es que this curve have no only length, but we have no width and height. It's just a curve. But this, no contradiction, que this curve is living in the three-dimension space, in the three-dimension context. Okay? However, a specification the T domain. The T domain is from 0 to pi because it's a closed figure. Okay, in this case, include both endpoints, no? 0 to pi. Okay. And now, if you want to represent like a vector value function, okay, no problem. R to any time is equal angular bracket 3 cosine t, comma 3 sine t, comma 4 minus cosine t, 3 cosine, sorry, 3 cosine t plus 3 sine t. Okay, I did well, yeah. This is the x component, this is the y component, and this is the z component. Super. Cool? Do you understand? What the hell? Oh, yes. Okay. And you know, in the teaching of the thing is super important, visualization of the thing. Visualization. Let me try to show you GeoGebra, at least in this example. And I bring more. Pero shit, I cannot explain it. Well, okay. I try to do at least. Okay. GeoGebra now. Okay. What's the problem? What is the shape of the graph? Call it again. Okay, 3D. Okay, you see the name, Mr. David. Look at that. Okay, wait a second. I close that. Okay, this is our famous space. But let me share. I forgot. I forgot to share that. Okay. Okay, David, look at that. This is the first surface. Bang. Do you see the name? What is the name of this? X squared plus y squared equal 9. You put like that. A cylinder, coño. And by the way, circular cylinder. They are parabolic. They are, bueno, but this is circular. And this is the plane. Boom. Do you see the plane? Do you see the plane? And the intersection, I can see a little bit que es Helix. The parametric equation that we computed before is this. Look at that. That's the surface. I copy curve, x component, like a vector value function, y and z. And the specification, the domain is 0 to 1. See, I want to see more clear. I delete the plane, I delete the cylinder, and you see, wow, amazing, our ellipse in 3D, que we can represent like a vector value function. Which one? That one. You see more clear? One more time I explain. Cylinder, circular cylinder. This is surface. Remember, this is whole, no solid. It's only the peel, the surface area. Two-dimensional object. Living in three-dimensional context. Plane, two-dimensional object. Living in three-dimensional context. Surface, two-dimensional surface. Living in the three-dimensional context. Now, finally, the curve is one-dimensional object because only have length. We travel around the ellipse. We have no width. The width is 0 and the height is 0. So it's just a rod, right? This is one-dimensional object living in three-dimensional context. Clear, 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 or confusing, confusing, confusing? Clear. Good. Okay, no problem, guys. I understand. I understand when I was a student. At the beginning, I don't understand very well this. But you need to use your memory to understand or memorize, identify is super important. Super important. Identify the surface. Okay, I spent one lecture doing this. Okay. Wow. Okay, do you see whiteboard?
Yes.
Okay. Let's do one more example. Let's do one more example. X squared plus y squared equals z. This is our first surface. Try to think in first name and last name of this. And c equal to x plus 3. It's another surface. Surface 2. And the curve I want to parametrization and using the vector value function is the intersection x1 intersection x2. Okay, again, what is the name, first name and last name of this surface one? That one. Any help?
Paraboloid.
Exactly. Paraboloid. In this case, you are more accuracy, you see circular because the coefficient is 1, 1. Coefficient here is 1, 1. Ese es paraboloide. Paraboloide. He said que es paraboloide. Paraboloide. What the hell? Paraboloide. What kind of paraboloid? Circular. Along what axis? Along
Z.
Along Z. Very well. Entonces, my paraboloid, I suppose, que look like something like that. Boom. Right? Good for you. Who are you, mister? Say your name.
Max.
Okay, super cool. And what about surface 2?
Is it a line?
Is it what? It's a plane.
Line.
No, line, remember. No. Some students say it's a plane. Okay, line in 3D, remember we study in parametric. When you see one equation like that, look, it's impossible to be line. Look, C is equal to X plus 3. You remember plane equation is AX plus BY plus C, Z equal D. Compare this and this. C, we have C. In this case, Y is missing, but I don't care because, you know, no necessarily in the plane is completely the variable. No, not necessarily. Okay, and the B is missing. It's 0, and A is 2, and D is 3, right? It's a plane. And line in 3D is X equal Y equals Z equal. You know that. Hello, right? Okay, entonces basically, the thing, the curve, I try. I know, I understand. I understand that at the beginning you know, but you have to remember. You have to. So you don't remember, you are in big trouble. Big trouble. Okay, so now the parametrization, well, I select, for example, I have no idea. I am totally lost. However, see, I put this and this together. I put x squared plus y squared is C is equal to C, but C is also 2x plus 3. There are no rule, guys. This is using your imagination. This is non-linear, and you know non-linear, the equation is always complicated. So it's x squared plus y squared is equal to x plus 3. Every example are different, and you try to manipulate this like that. Look, this is x squared minus 2x plus box plus y squared equal 3 plus box. And the complete square here is obvio que 1. Entonces x minus 1 squared plus y squared equal 4. Okay, entonces easy to declare que this is, no, you divide by 4, obviously. Divide by 4, obviously. And we have x minus 1 divided by 2 squared plus y over 2 squared equal 1. Okay, entonces yo declaré que x minus 1 over 2 es cosine t. Yo declaré que y over 2 es sin t. Therefore, x alone is 2 cosine t plus 1. Nice. And y is equal to sine t. And what about z? We need z. C is easy. You take here this equation is easier. And c is equal to x, pero who is x? S is x. Entonces multiply by 2 is 4 cosine t. Cosine, no contañe. Hello. Cosine t plus 2, ¿no? Plus 3. And 2 plus 3 is 5. Likewise, unbelievable. The time fly. Now, this is the 1, 2, and 3 equation. Parametric is obvious in this case. A closed figure t vary from 0 to pi, and the vector value function is r of t vector is equal bracket angular bracket 2 cosine t plus 1, comma 2 sine t, comma 4 cosine t plus 5. Close. And t vary in this value. This is the way to express vector value function. Wow. Well, let me show you one more time the algebra. Okay, it's important because my objective is also integrate everything Okay, you are familiar with the surface. But it's up to you guys. You are familiar with the surface, and you see now the new thing is the parametric, no? Parametric. There we go. Okay, 1 second example. Okay, let me see you see or no the GeoGebra. Do you see? No? Yes, okay, super. Okay, now, well, this is, look at that. This is my first surface, parabolic, cylindrical, by the way. Look at the cylinder here. And this is another plane. No line, plane, coño, right? Okay, now the intersection is the curve. I found the parametry. I copy here. Bam. Do you see now? Clear? You say always a helix? No, always, no, of course no. In the majority of X scenario, yes, when you have the typical surface is quadratic. Yes, but no, not always. Not always. Okay. Now, no. What's the next? What is the next? Well, and the time that we have is only 5 minutes. I want to explain another thing. Wow. We need 5 hours in the lecture. Do you see what bar? Okay. So now I have a lot of examples of this. Unfortunately, we have no time. However, you see, bueno, professor, entonces, what is the idea for the parametrization? What is the best way for doing the parametrization? There are no best way. There are infinity possibility. However, the mathematician discovered, we have 5 minutes, yeah. It's enough. No, it's not enough. But the thing I try to explain. Okay, one fantastic way to parametrization is using the R length. R's length. Some mathematicians say, well, okay, parametrization is you can use any parameter, T. However, why not using R length like a parameter? Now, what is the advantage and disadvantage of this? So what is the idea? The idea is R length is distance. We call L, but R length is integral from A to B, the absolute value of the derivative of the vector value function, dt. However, if you suppose S is the integral from A, okay, the first point, to T, and put no numbers, and variable T in general. And you put here, in order to don't confuse the T inside the integral, you put absolute value R prime in U, du. It's the same. This is dummy variable. U is dummy variable. But when you integrate, so find the antiderivative and evaluate, so the define integral, you have a function of T. Actually, what is the idea? The idea is, okay, we have S as a function, it's a scalar function, depending of T. And what is the magic of this? When you have a curve, suppose, and you parametrization using R length, suppose that this is my point. You travel for this, and the parameter is this distance. Suppose S equal 1. Suppose S equal to, no T, sino es the R length. Entonces es la que, you imagine like one insect moving, travel along the curve. Entonces super easy si you have the parametrization, use R length. Well, entonces you find the position of the in the insect, pero no using T, because I have no idea what is T. T is a time, an hour, in second. No. The insect travel distance 20. So I don't know how many rotation, how many time. I don't care the time. I care only the distance. I suppose that the insect in that moment 20. Maybe it's in this position, x equal 20. Because I want to investigate what is the x, what is the y, and what is the z position for the insect, like a position vector, no? Do you understand the idea for the parametrization? Okay, so let's do it in one famous curve, que es the Helix. The Helix is similar to this. Helix. The Helix. What is the parametric equation for the Helix? There are many Helix. However, I want to copy one easy, que es cosine t, sine t, and t. Okay. This is, you know, a circular. Suppose que you ignore the C part. This is a circle, yes or no? In 2D. But in 3D, no, because you increasing the height. Entonces es el helix, like that. If you want, I show you in GeoGebra, super clear, the helix. Entonces now I take this example, the helix, this example. They want to parametrization, the helix, no using T. So T vary, for example, I don't know, in between 0 and 6 pi. Because not to pi, because I don't want only one revolution. No, I want several revolutions of the helix, right? Everyone follow me the idea? Now, okay. Okay, then I compute the velocity, que es the derivative of this. And the derivative is derivative cosine is minus sine, and derivative sine is cosine. And derivative t with respect to t is 1. Entonces this is the velocity vector, and the speed vector, que es the magnitude of this, is square root negative sine t squared plus cosine t squared plus 1 squared, que es 1. You know very well que sine, negative sine squared is positive sine, and sine plus cosine is 1, and 1 plus 1 is 2, and the speed is radical 2. Wow. It's like the insect travel and the constant speed. Now you find now the R length parameter, que es the integral from 0 to t of this, que es radical 2, no? Radical 2 du. Wow. Radical 2 is a constant. I put outside the integral. I integrate the u with respect to u is u, evaluate in between 0 and t. The answer is radical 2t is equal s. Now t is s over radical 2. And you replace in the original equation of the Helix, que es parametrization using the t. No. I want to find the parametrization using s, que es the R length. Entonces I replace R of s is equal. Entonces now you're right. You're right, is cosine of t. Pero who is t? T is s over radical 2. Comma, sine is t is s over radical 2. Comma t, que es s over radical 2. And this is the parametrization of the Helix using t, using s, sorry, R length. Advantage and disadvantage. Well, you see maybe next time of the parametrization use R length. Let me anticipate something. Advantage is, you know, the speed is constant. Normally, si you compute the speed of this is 1. Ese inset, pero que travel slow along the curve. Slow. If you want to find the position of the inset, you evaluate in the arc length. Suppose I want to evaluate at s equal radical 2 pi. So the inset travel this distance along the helix. Entonces, you evaluate this in radical 2 pi. And use radical 2 pi. Entonces, the answer is -1, 0, pi. That means that our inset is located at x equal -1. In this moment, I take a picture when they travel this distance along the helix, y is 0 and c is pi. Disadvantage of the arc length parametrization. Wow, sometimes it's very complicated. I select here the easy example, but sometimes it's crazy because the antiderivative, you know, in calculus 2, the antiderivative of the some function, so some function have no antiderivative. It's impossible. And that's the reason that the teacher in calculus 2 explain numerical method. Entonces, no, entonces it's impossible doing this. Entonces now, advantage and disadvantage. It's easy to visualize. The equation that we study next time is easier in parametrization use arc length. Disadvantage que not always is possible. Entonces we need to know this tool, but not always we can use. Okay, guys, entonces now stop too much. I need 2 hours more to continue, pero no. We continue Wednesday. I suppose que the review we start, because I don't finish. The review maybe, let me stop recording.